The density-based solver is applicable when there's a strong coupling or interdependence between density, energy, momentum, and/or species. There are two versions of the density-based solver: the coupled implicit density-based solver and the coupled explicit density-based solver. The implicit option is generally preferred over the explicit option because the explicit option has a very strict limit on the timescale size that you can use because of CFL constraints, which there's not such a constraint for the implicit option. Examples where you would use the density-based implicit solver include high-speed compressible flows with combustion, hypersonic flows, or flows with shock interactions. The explicit option is really only used for cases where the characteristic timescale of the flow is on the same order as the acoustic timescale, and examples of problems like this could be the propagation of high Mach number shock waves or shock tube problems. This slide describes solution controls associated with the density-based solver, and the primary solution control is the Courant number. With the density-based solver, there's a pseudo-transient term that's used even for steady-state problems, and the Courant number is what's used to help determine the pseudo-time step size. You can also use the pseudo-transient option, and then the inputs are the same as we saw in the earlier slide. For the density-based explicit solver, numerical stability constraints impose a maximum limit on the Courant number of 2. For the density-based implicit solver, there's no numerical stability constraint in theory. The default value is 5. For startup, you may need to reduce this to somewhere in the range of 0.1 to 2. And for external aerodynamics applications, values of 100 to 1000 would be common. There's also an option called solution steering, which automatically adjusts the Courant number as the solution iterates so that it has an optimal value at all stages of the calculation. There's an example of the use of solution steering in Workshop 4, and additional details about the solution steering procedure are available in the appendix of this lecture.